Yeah. Okay. Thanks very much. I'd like to thank all the organisers for today. It's been a really lovely workshop already, and to CREST in particular for the financial support and coming to be here to speak to you all. And I'd also like to thank my collaborator and host here in Japan, Masanao Ozawa, for a really wonderful trip so far. So I won't be talking about consciousness directly, but I think the various connections to consciousness have been posed for the kind of material I'll be talking about today. It will be talking about these what's known as quantum cognition, which is an approach to modeling various psychological effects that have been found in humans using quantum theory, and looking at this through the lens of category theory. Great. So various effects in particular in the way that people respond to being asked questions and so on, such as order effects, have been explained by going beyond what you normally use as a conventional classical model, which is often just called a Bayesian model, and instead using some aspects of the mathematics and quantum theory to model cognitive processes. This is a classic book on the subject by Ritsumeikan and Fusa. So importantly, it doesn't require supposing that these models arise from quantum physics in the brain, so that may or may not be true. But the idea is more to use the mathematics of quantum theory as a sort of high-level language for modeling cognition itself. But in physics, whenever we use quantum theory, there's often a lot of effort put in to justify it. And I think with this approach as well, people quite rightly ask whether we really need to use quantum theory to talk about all of these effects and so on. And so we want to know what the role is of quantum really in these cognitive approaches. So I think I'm sympathetic to these quantum approaches, but I'd like to give them a really strong argument to see where they come from. And to do that, I think we need a nice theory-independent way to talk about these kind of models that come up in psychology and compare these classical and quantum models and so on. So I think a nice way to do that is to use the language of category theory, where you can work in this very theory-independent way. And in particular, you can work quite intuitively with what are called string diagrams, which is what we're talking about today. So we're going to give an approach to talking about these aspects of cognition in terms of string diagrams. And then we'll use this to talk about some of the claims about using quantum models in cognition. And I should just say this is very much work in progress, so we won't get to the end of the story here. It'll kind of end on a cliffhanger. But yeah, come with me on the journey. So I'm going to start with talking about the mathematical aspect, and then we'll get to the more cognition-based approaches. So formally, what we're doing is working with what's called a symmetric monoidal category. You can think of this as a kind of universe of interacting systems and processes. So the systems are normally called objects, and the processes are called morphisms. So we might have a morphism F from A to B, might be written like this normally. You think of this as a process. It takes in something of type A and returns something of type B. Luckily, we only need to work with two sort of heavy mathematics today, because we can just use this nice formalism in the string diagrams, and it's still mathematically rigorous, but it's just kind of easier to work with. So here we draw a process as a box now. So you have an input wire for A and output wire for B. So the diagram's always read bottom to top. And what you can do in the category is you can compose these things, you can plug them together. So if I have another process from G, from B to C, we can put them together in sequence. Also, if I have a process G from C to D, so it has different types, what we can do is combine them in parallel. So we can combine our objects using this feature known as the tensor, and also our processes using the tensor to build this new one. Most of the time, we won't have to really use this tensor symbol, however, because in diagrams, you just draw them running in parallel. And you can really think of this as just two processes, F and G, acting separately with separate inputs and outputs, and they're just running in parallel. So from these two operations, you can build these more general string diagrams that we'll see in the talk. In particular, formally, basically, there's an object that corresponds to empty space in the diagrams. What this really lets you do is have processes that don't even have an input, and these are called states. So these are quite important. So a state of A is just represented by a box with a wire for A and just nothing coming into it. So this is called a state, and it's just like saying we don't have any kind of input system. We just start knowing that A is in some given state. And the final thing we'll use in the pictures that we'll see is the ability to just throw systems away as well. So when you see this ground symbol, it basically means ignoring the system A, but this is called discarding. So it's like throwing it away or just not thinking about it. And there's this rule that basically all the processes we'll talk about in this talk, you can assume form what are called channels, which means if you have the process, but then you just throw away the output, then you might as well just throw the whole thing away. So that's this equation. Essentially, everything will satisfy this property though. So I've just said what the diagrammatic components are now. And the point is that you can instantiate them, give them semantics in many different categories. So it could be that these boxes are just like the wires are just sets and the boxes are just functions between them. Or they could be more generally processes in some theory of physics. For those who are familiar with the mathematics, this slide will talk about what the model really is for treating these quantum and classical models. But I'll just try and give intuitions for everybody so that we can still follow conceptually. So we're working in what's called the category of finite dimensional C-star algebras. So the objects in our pictures would be these mathematical objects called C-star algebras. These basically just let you model classical physical systems and quantum systems together. So both of those things form C-star algebras. And the boxes would be what are called completely positive maps, for those who know about these. And in particular, the channels I wanted to trace preserving. So this is just the standard notion of a physical operation between these kinds of systems. So it could be quantum with quantum operations, or classical probabilistic ones, essentially. Discarding corresponds to trace, for those familiar with quantum formalism, which is just the way you talk about marginalizing out systems, essentially. And the states correspond to positive elements, which you can think of as being like states of your algebra, at least in finite dimensions. So in particular, you might have what are usually thought of as quantum systems. So it's a Hilbert space, H, and the algebra would just be the space of linear operators on H, which are like the observations you can do in a system. So now the point of this is just to say that a state would really just be a density matrix. These are the normal notion of a quantum state on a Hilbert space. For those who are not familiar with mathematics, the point is just that you can include classical and quantum processes together in one category, which will be useful to us. And as I mentioned, you could work in lots more settings. So it could just be sets and functions or some other theory of physics. Yeah. The final other aspect we use is, okay, we've talked about how you could have quantum and classical together here. When you're talking about these aspects in psychology later, we'll need some notion of classical systems themselves to be explicitly represented. So when we know something is classical, like when it's just a piece of information that would read out of an experiment. So we'll have a special notion of what we call a classical object, which you can think of as just a finite set. And the difference is that we're drawing these thin wires, so hopefully you can see that this wire is thinner than the ones we saw earlier. So whenever it's a thin wire, it means it's classical. And the key thing that you can do classically is that you can copy information. So there'll always be this copying map around on a classical system X that just literally lets us copy that state of X, where X is this finite set of states. So for those familiar with C-star algebras, these correspond to the commutative algebras. It's normally how you talk about classical things. More conceptually, if you have one of these thin wires and you have a box like this and it's a channel, this is just a probability channel between us. So just something that sends each thing in X to some distribution over Y. And in particular, the states are just probability distributions. So this lets us embed classical kinds of processing inside our pictures. And we do that by just drawing these thin wires instead of the thick ones. So we'll see more of these diagrams as we go, but I think now it'll be more interesting to go to the actual cognitive aspects. So we'll talk about the kind of setups that people consider in quantum cognition now. So often what it is we have loads of participants and we're asking them questions. And each question has some finite set of answers, usually just yes or no. And the data from the experiment can be thought of as giving probability distributions over their sequences of answers. So I might ask them question A, then question B, and I might say like yes to the first one and no to the second one. And we'll get a distribution telling us how likely it is that they would answer in each of those sequences. So a famous example is this Gore-Clinton data set. So the question A would be, do you generally think that Al Gore is honest and trustworthy? This is in the context of the US election years ago. And B would be the same thing, but with Bill Clinton instead. So if we call the answer to the Al Gore question X and the one to Bill Clinton Y, the answer, you would obtain this distribution here over the sequences of possible answers, right? So something like AYBN would mean they said yes to the Al Gore question and no to the Bill Clinton question, or ANBN means they said no to both. And this will give us a probability distribution. In the diagram, it just looks like a box, like a state of answer to the first question and answer to the second question. So we'd have various, like a few of these distributions around from our experiment, like we might have asked BA in the opposite order. So we asked them about Bill Clinton first and then Al Gore. And to give the game away, we might already get a different distribution here. So we can get certain effects, like these order effects that we'll come to in a minute. So a model now would be trying to explain how these probability distributions come about in terms of some underlying mental states. So a question answer model is going to be back in on our category that we started from. It's going to give us some object that models like the participant's mental state, which is hidden from us, you could say. Now, each question can be thought of as a process or a channel of this form. So this would be like question A, like the Al Gore question, let's say. So we start in some mental state as well. So the participant is just there. And we ask them the question, and then okay, they'll be in some new state potentially now after the question. But also we'll get some classical information out, this X, that would just be down. So it could just be, you know, yes or no, and generally it could be from some finite set. So a question is quite naturally modeled as this kind of channel where you have your general system going in and out that models the agent, and then information about that answer coming out on the left. So this kind of thing we call an instrument. So A is the instrument on our system S, and these X are the classical outcomes. And Ozawa and Krennikov wrote about how you can apply quantum instruments in particular in these quantum cognition type experiments. And here we're generalizing it to more general categories. So just to give an example of what kind of models you can get, we should talk about what kind of thing these instruments can be. So in the category we care about, this finite dimensional C-star algebras one, they're, for those who know the formal stuff, they're given by a set of completely positive maps where the sum needs to be a channel, so it needs to be trace preserving. So there are these maps AX indexed by the different answers they might give. That's the little x. In quantum cognition, people basically always, well, not always, but most of the time, they just talk about projective instruments. So these correspond to projective measurements in quantum theory, which are kind of the most simple form of measurement, but not the only kind of measurement in quantum theory, where you project your Hilbert space onto some different subspaces. But something that comes immediate in this kind of approach is that, you know, you can work more generally with other kinds of instruments. So a general one of these on a quantum system, it's Hilbert space, is just what's normally called a quantum instrument. So this is just like the general notion of a measurement on a quantum system. It doesn't throw it away. So the quantum system comes in, and there's some new state at the end, and then we get some classical output. But if we think about these classical objects, we can have general classical instruments would look like this now. So it's just a probability channel on our state space S, even if it's classical, let's say, where you get some outcome as well. But it could be that the state here changes. So it doesn't, just because it's classical doesn't mean the state is left alone. Generally, when people consider classical models in this kind of work, they just use what I would call a non-disturbing classical instrument, where we just take the state and we copy it, so we don't change it. So just assume that classical means non-disturbing on the state. And then we just read some outcome out of that state like this. So we'll call these non-disturbing, but you can model much more if you allow these more general kinds of classical instruments. So to come back to our setup now, we were modeling questions like A and B with these instruments. And what a model needs to do is recover the data from the experiment, right? So for each distribution over answers, so this is by asking question A and then B, and this on the left was our distribution in the data, we need to get that back. So we need to say that the participant starts in some initial state, that's generally fixed amongst all the sequences. And then we just model that process, asking the two questions by first applying the question for A and then the question for B. And we throw away the system at the end, that's just discarding that at the top. So this thing on the right is now just a state of X, Y, and this needs to be the same as the distribution we started from. More generally, you can imagine having lots of sequences, whether it's like ABC or whatever, and you have to plug them in and recover that data. This language becomes quite nice for describing the different kinds of psychological effects that people have studied in these setups. So one of them would be an order effect. So we can say that two questions are an order effect, when basically, as we saw with the Clinton-Gore example, it might be that asking the first question, A and then B, gives you different answer probabilities to asking B and then A. And that just corresponds to this kind of string diagram here, where you can see we've got A and B swapped, and we throw away the system at the end because we don't need the hidden state anymore. So these kind of things were used to argue for quantum models, because if you use these quantum projective instruments, you can get these order effects. Like if you take Z and X basis measurements on a quantum system, these don't commute, and so you can get these kind of interesting order effects out of them. And if you use these classical non-disturbing ones where you just copy the state and you don't change it, you won't be able to get any order effects because the state's left alone and just like reading off facts about it. But if we use these more general kind of classical instruments we saw earlier, where the state can change, in fact, you can get these kind of order effects. So I think this is a bit unappreciated. Another example of an effect that's a bit harder to treat quantumly actually, but not impossible, are what are called response replicability effects. So this is if I ask you question A, then question B, and then question A again, you're unlikely to give a different answer to the two question A's, maybe because you just remember what you just said, or so on. So you're going to say the same thing both times, often. Though there would be scenarios maybe we don't, but this often comes up in experiments. So this just looks like this in string diagrams. It's saying, okay, you start in some state, we ask you A, B, A. This says, well, I may as well just ask you A and then copy your answer because you're just going to say the same thing both times. So these effects for quantum systems, if you use those projections, you're only going to get this property if your projections commute. So you won't be able to get order effects at the same time. This caused a problem for the way the quantum cognition literature was working with using these projective instruments. So this is one reason why you want to use general instruments on quantum systems. But if you do that, then you can get these kind of effects, either classically or quantumly. So again, they don't pin you down to having to use quantum. Now, final one I just mentioned is one that really was invented specifically in the context of quantum cognition from Wang and Ritsumeikan and others. They call the QQ equality. So this is something they observed in a lot of data sets for these question answers. And they proved it holds for quantum systems. So now if we just have questions where the answers really are just yes or no, we say they satisfy the QQ equality when we have this equation in the probabilities. It says, if I just look at when people say yes, yes, or when they say no, no, so they give the same answer to both, then the order doesn't matter anymore if I add those up. So if I do yes, yes for and no, no for AB, it's the same as doing it for BA, where I reverse the order. And you can turn this into an equation in string diagrams. This closed diagram on the left would just be a probability, and it would be this one at the top here. And this one on the right would also be a probability. You just have to introduce this extra feature where you can bend wires up here, and this basically just checks that the two answers are the same. So this does hold for all quantum projective instruments, and they use this to say, well, therefore, quantum stuff's going on here. But I think that argument doesn't really hold up because, I mean, it's a commutativity statement, so it will automatically be true classically anyway. Classically, these non-disturbing instruments always commute. So it's not really a unique feature of quantum either. And it can hold or cannot hold if you use general instruments, however. So, to strengthen what we've seen so far, Ozawa and Frennikov showed that they could actually build essentially a classical model, and in fact fully deterministic when in terms of the instruments, which fits this Clinton-Gore data set we saw and shows all of these effects we talked about. So it has order effects, it has response replicability, and it satisfies this QQ equality. I don't think it's worth going through the proof in too much detail, probably. How am I doing? Yeah, I think it'd be better to skip that, but you can ask me about it at the end if people are interested. The key point is just that you build a classical instrument for both A and B that's fully deterministic. So it's just literally a function, and it's defined in quite a simple way. So obviously you need to change the state of the classical system when you ask the question to get these kind of effects, but it doesn't have to be particularly complicated or it can just be working on simple finite sets with some updates. And to make this even stronger, we can basically show that almost any kind of data that comes from these question sequences can be given a classical model, in fact. So the way to show this is to turn your whole data set, which was these many distributions before, into just one channel. You think of it as like your choice of question at the bottom, and then your answers to each question at the top. So given a choice of questions, it gives us our probability table before. And if you think about the fact that this arose from an experiment, you can justify that it should have this property that means the inputs for later questions shouldn't affect your answers to earlier questions, right? If they did, it just means there's something wrong about your probability tables, essentially, because it's meaning the answers people are giving are being influenced by what you're going to choose to ask next. And any instrument model you can give will always have this property. If you make this assumption, you can prove either in string diagrams or just conventional probability notation that any kind of sequential data, question data setup with this property will have a classical model. So particularly if you have a quantum instrument model, you can get a classical one as well. So the key thing was just to use this slightly broader notion of a classical model where the state can be changed as you're asking the question. Like this is the key aspect. So at the moment, this looks quite damning for the quantum models. I'm actually quite sympathetic to quantum approaches. I just would like to build very strong arguments for them because I think then it would have a real impact, whereas those coming from quantum foundations often are a bit skeptical of the use of the quantum formalism. So just to sum up what we saw, we basically use this categorical approach to broaden the kind of models you think about in these cognition setups. So we can strike both classical and quantum models together, and also helped us broaden our view of both of those things. So in quantum, it leads to these general instruments. Classically, it leads to this broader notion of model where the state can get changed while you're asking the questions. And these are basically what you need to give all of the kind of effects we saw. And in G, they'll always work for any kind of data given just by simply asking sequences of questions, and that's it. So what would we actually need to get something where we did need quantum? So I don't have a knockdown proof yet, but I think that basically what you want to do is have more structure in some form. One thing you can do is include like order structure in your questions. So for example, quantum approaches have been used to model these kind of fallacies, as it were, in the way people reason. So many people might have seen the Linda bank teller example where people would judge this conjunction on the right to be more likely than the one on the left, even though logically it's a subset of that on the left. So these approaches have been studied using quantum models, and I'd like to sort of look at those next and see if the case holds up there. Most interestingly, I think, though, is that what we really need to do is go beyond just thinking of one agent and we're just asking them questions in sequence. This is basically sequential. I think what you want to use is actual compositional structure, meaning parallel structure. So to do that, you have to impose a bit more structure in your model. You have to make some assumptions about what the hidden space looks like. So essentially, instead of having this one wire, we now have something like these 3 wires. This makes me think of the use of domains in conceptual spaces theory. Those familiar with it. So that's just where this little example came from, where you might have like a food space in your mind that's composed of domains like color, taste, and texture. That could be anything depending on what the questions are about, obviously. So you might want to explicitly impose that you're going to model these different domains in the setup. And then you might be able to use the tensor that's there in quantum theory and some more uniquely quantum features like entanglement, because these are the things that have led to Bell inequalities in physics, where these are the ways you really prove that a system is behaving in a quantum way. Finally, you might just want to go elsewhere in cognition, obviously, and model something other than just these sequential scenarios. So there's other cases where the quantum formalism has been applied. So as I mentioned, it's a work in progress. I'm interested in pursuing all of these aspects further in future to see if there are cases where we can really give a knockdown argument for using quantum models. But for now, I'd like to discuss with you all, so thanks very much.
Okay, so with the questions, audience, do you have any question or comments? Nicole. That's a possibility. This is a relevant question because I have to run to get some official documents. But so effectively, what is this about? You can you could, if you look at this category, you could replace quantum effects with the classical models when we're explaining consciousness.
Well, I wouldn't say it's explicitly about consciousness so far in this work. It's really just modeling these question answers. Yes. And it's not a generic proof that there's no reason to ever use a quantum model. It's saying if all you have is data that looks like tables of just like the probability of answering the questions in sequences, like would you say yes, 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 or yes, no, no, then you will be able to give a classical model for that. So you won't be able to get this really hard proof that you just have to use quantum model, whereas something like a Bell inequality in physics would be basically saying you can't have a hidden variable model classically, and you have to use something quantum. So it rules that out, but there'll be other, I think people are sort of aware of this, but not fully aware in all of the people that know about quantum cognition. So they would make other arguments for using quantum models normally, which I think are worth thinking about. So they would use either just that the quantum model is more elegant, or they would use some of these features I talked about at the end. So it's not a proof that you should never think about a quantum model. I would just like to give a really solid case. So for these kind of effects on their own, you can solve them classically. Thanks.
So to implement the compositional structure, how would the experiment look like in practice? So it wouldn't be sequential question, right? Would it be like if I presented 3 color, taste, and texture, and then you ask something that relates to 3 at the same time, like how similar?
Yeah, I think. Sorry.
I just wanted to know how
the
kind of question capture.
Yeah, I mean, I think you could do many things basically. So I don't have some specific proposal here. I just drew a sort of illustrative picture where at least we can see that the state space is factored now. So I just think it would have to involve an explicit assumption that there are different aspects of cognition going on, and then processes between those. So it wouldn't have to look like just these instruments and sequence anymore. It probably should look different. But I don't have sort of one answer about what it could be. Draw some graph or a diagram that relates them. And yeah, so
like probing, like the pairwise similarity would necessarily be insufficient, or it could principle.
I think pairwise could potentially be enough. Yeah, you might only need to ever think about 2 things at a time. Yeah, that's a good thought then.
Here. Thanks for
Thank you.
Is there a sense, following up on your point about elegance, is there a sense in which formalism, you can use formalism to compare the complexity of the classical versus quantum model in some way? So,
I think it makes sense to compare complexity, yeah, if you want to make a case for elegance. I'm not sure that this diagrammatic approach particularly helps with that. It just gives you a way to even give the definitions uniformly for both. And then I think to talk about complexity, you'd have to work concretely in both categories at that point. So I wouldn't know a way to do that in pictures. Not to say it can't be done, but yeah, I wouldn't know. But it's a good thing to do, I think. Thank you. Thank you.
I maybe ask a very simple or fundamental question, but just want some clarification. So is everything you're saying about based on the assumption that the state will change over time? So let's assume the state somehow never changes over time. We just still say that whatever you get from the measure will still be dependent on your sequence.
Yeah, thanks. Yeah, basically, if you assume the state never changes, I would say the way I would assume that would be something like this non-disturbing instrument here. So that's saying that there is an output state, but it's given by just copying the input state. That's what the white dot is. So it hasn't changed, basically. So if you just assume that, then you won't be able to get all of these effects, like the order effect you won't be able to get, basically. You could have this one, because it just says things are consistent, so that will be fine. But mainly the order effects are the challenges. Yeah.
Yeah, so in the longer term, I guess, are you hoping that the category theoretic approach will provide a more formal way of talking about decision-making theory? And if so, I mean, if you think that it would provide like a formal language, could you imagine that the people would eventually, the way they do it is MCAP programming language, so you can also program category theoretic approaches. It's not very much speculating into the future here, but if we build a formal model of decision-making theory in this manner, that people could also then begin maybe programming it in easier manner.
Yeah, thanks. Yeah, system. Yeah, I think it makes a lot of sense to do that. And I think decision theory is like a big area in itself in computer science that I'm not totally familiar with, but I've seen various papers in the applied category theory community that are modeling it, usually like meaning probabilistic decision theory, I would say. But I think if it's, as long as decision theory means some quite intuitive notions of like this person makes this decision and then this happens and so on, then this is the kind of thing that categories are pretty useful at modeling. And yeah, if you want to model it in a theory independent way, I think they're good for that in like these sorts of approaches. And because they do so in a sort of formal, discrete way, they would help you program. Yeah. So I don't know enough about decision theory to know what remains to be done basically as it were, but maybe you do, maybe you know more about what needs to be done in this approach, but yeah, it makes a lot of sense.
Just wanted to follow up on. I have a feeling that most of these things that you heard are like paradigmatic cognitive things, right? So
yeah,
things like order effect, it's hard to really, it's not clear whether they exist in consciousness. Other effects that you have also not quite clear whether they're transposed to consciousness. So I just wanted to know how broad you want to understand your approach. Do you think that they also like directly apply to consciousness, or would that be
yeah,
maybe a different kind of approach?
yeah, I think it would make sense to apply this kind of formalism to setups where you're asking for judgments about phenomenal aspects. So the same approach could be used. A separate question of you know, just the formal aspect of using the categories and so on, I think would make sense. I mean, you just need experiments where there's a participant and there's some output that we get. But whether that means the quantum models particularly are good for that, whatever, is another question. I know now has thoughts and a proposal about this, so I'm looking forward to talking about that in more detail later. So I'm not as familiar with that as to the claims that have been made about consciousness in particular.
Yeah,
you could add a bit if you like.
Yeah, just to add, so most of the applications of quantum computation so far have really cognitive domain, right? Like decision making, concept, memory, and so on. And I briefly talked about the similarity judgment itself has also order effects, even at the level of color, right? So that's a starting point, but still not really, as Sean said today, order effect is not necessarily the definitive proof that you need to go to full quantum. Classical with this kind of branching is also possible to explain that. And we also don't have a definitive proof of the violation of the very important thing in the, let's say, backward masking or Pinocchio rivalry or also sparring paradigm or things like that. And if we start to have something like that, then maybe we start to have a doubt that also terminology may have this kind of structure as well, but it's not there yet.
But I think it's, if I may also,
Yeah.
like I think it's also very important to find out what is exactly what we model. Are we modeling the judgments about consciousness, or are we trying to model consciousness based on the judgments? I don't think these are two very different things.
Yeah.
Thank you.
Yeah, I think a priori it seems like we're modeling the judgments. I would say like this channel sort of is the judgment, as it were, but probably your model behind it would assume some kind of underlying model of the consciousness itself. But I agree, it's a good subtle point.
Yeah, last good question.
So entanglement seems to be a really special motivation for applying quantum models. Can you provide an example of how entanglement may show up in the models that you've been working with so far?
Yeah, sure. I mean, something that comes to mind is just if you have, if you want to have sort of two different aspects in one of these sort of cognitive models, maybe two different modalities or something like this, but you want them to be some concept that maybe relates both, but yeah, it doesn't just come down to, it comes down to some relationship between both. You can model this as an entangled state on them, essentially. Yeah, very speculatively for in experience or something, maybe use it for a synesthetic type of state or something between two modalities. But just generally, you can, so if you just have a state of two wires like this, if they're classical, that could still just be a classical correlation between them, but not in this extra thing of entanglement. If it's a quantum state and it's a pure state and it doesn't just split, then it'd be entangled. And yeah, it gets quite subtle talking about whether you need the entangled thing or not, but this is what Bell inequalities would help with. So you kind of need to model a correlation between two aspects of cognition and then prove something like a Bell inequality, I think. Thank you.
Yeah, again, maybe brief comment, but we rarely, in science physics, we rarely prepare some kind of object with multiple features and then ask two aspects at the time, right? Have you ever done this kind of experiment, or have you ever seen this experiment? Probably not, right? Usually, like after two, features and we measure one at a time or both. That's it. But to specifically test this kind of, idea, you need this type of experiment. So almost nothing is known about whether this, kind of prediction holds on.
Yeah, thanks.
Thanks a lot, Sean.